Let's look at another method to solve non-homogeneous ODEs. While undetermined coefficients is a useful method, it has the drawback that it requires a lot of computations and it requires you to have a good guess to start with. On top of that, it requires your right-hand side, the non-homogeneous term, to be in a specific form such that you can start guessing. What if that doesn't happen? We do have other methods. This one is called variation of parameters and is the one we will see this week. The goal of this method compared to uncertain coefficients is the generality. We want something that can handle something like our example, y second plus 3y prime minus 4y equals exponential of 2t divided cos of 2t. Undetermined coefficients cannot solve this because our right-hand side is not in the form we want it to be. It's, instead of being a product of things or a sum of things, is a fraction between two things we could solve for. So in this method, we're going to first solve for the homogeneous ODE, and then we're going to build on that to solve for the non-homogeneous ODE. So the first step is solving y second plus 3y prime minus 4y equals to 0. And we can do the calculations, and the general solution for this is c1 exponential of t plus c2 exponential of minus 4t. And the idea of the variation of parameters is that the solution of the non-homogeneous problem is a variation of the solution of the homogeneous problem. So if we have the solution of the homogeneous problem being c1y1 plus c2y2, the solution of the non-homogeneous problem has the form y1 plus y2, but the coefficients now are functions of t themselves. So we have u1t times y1 plus u2t times y2. Can we just plug y in and solve? That doesn't work because we have now introduced two unknowns, y1 and y2, but you only have one equation. That means that we have at some point a choice to add a new constraint. Usually this is made such to help us out and to make matters a bit more simple. So we're going to try to find the best situation in which you can add this choice and simplify our work. So let's go for it. We have y equals u1 y1 plus u2 y2, and we have y prime that is u1 prime y1 plus u1 y1 prime plus u2 prime y2 plus u2 y2 prime. And we impose as extra solution, as extra constraint for u1 and u2, that u1 prime y1 plus u2 prime y2 is equal to 0. So specifically for our case, what we're imposing is that u1 prime exponential of t plus u2 prime exponential of minus 4t is equal to 0. Can we do that? Is it all right? I'll let you know that it is, that we can do it and it is all right, but we are skipping some statements about why it is. Then with this, we have that our possible solution, capital Y prime, is equal to y1 exponential of t minus 4 y2 exponential of minus 4t, and y second is u1 prime exponential of t plus u1 exponential of t minus 4 u2 prime exponential of minus 4t plus 16 u2 exponential of minus 4t. We don't have everything new to solve through the extra condition we just imposed. Then we take the non-homogeneous ODE and we plug in everything that we have built until now. And this is a big blob, but we want to take away, put together all the coefficients of u1 and all the coefficients of u2. So we retrieve u1 prime exponential of t minus 4 u2 prime exponential of minus 4t plus u1 exponential of t plus 3 exponential of t minus 4 exponential of t plus u2, and within parentheses we have 16 exponential of minus 4t minus 12 exponential of minus 4t minus 4 exponential of minus 4t. And all of this, we want it to be equal to exponential of 2t divided cos 2t. And if you notice, the two parentheses that we just introduced are equal to 0. So we now have an equation that only has y1 prime and u1 prime and u2 prime, and has some exponentials on the right hand side. So if we put this together with the constraint we imposed earlier on, what you notice is that this is an algebraic equation. What does it mean? It means that we can solve it using algebra. And the unknown of these equations are u1 prime and u2 prime. And we can solve things out, and we have that u2 prime satisfies 5 u2 prime exponential of minus 4t equals minus exponential of 2t divided cos 2t, and u1 prime satisfies u1 prime exponential of t is equal to 1/5 exponential of 2t divided cos t. That means that u1 and u2, we can just solve them by integrating these equations. So we have u1 being indeterminate integral of 1/5 exponential of t divided cos 2t dt, and u2 is equal to minus the indeterminate integral of 1/5 exponential of 6t divided cos 2t dt. So a particular solution will be based on these integrals. A particular solution will again have the form u1t y1 plus u2t y2. So the general solution is a particular solution plus a homogeneous solution. So we have some coefficients of y1 and y2 and some integrals. Notice that from the particular solution to the general solution, I assign specific bounds to the integrals. That means that you are giving a component to C1 and C2 is popping up by assigning these bounds. We still have two coefficients, as we would expect. So generalizing this approach, to solve non-homogeneous second-order linear ODE, we first find the general solution of the homogeneous ODE. So we're setting y second plus pt y prime plus qt equal to 0, and we get the homogeneous solution, the general homogeneous solution being c1 y1 plus c2 y2. Then we assume that the particular solution has the form u1 y1 plus u2 y2. As in the example, we can take the first derivative and the second derivative, but in the first derivative we assume that y1 prime y1 plus y2 prime y2 is equal to 0. Then the first derivative simplifies to only 2 terms, and the second derivative simplifies to only 4 terms. Not going to read them aloud, but it's a combination of first and second derivatives of u1, u2, y1, y2. And we plug this information in our differential operator. So we have y second, that is u1 prime, y1 prime, plus u1, y1 second, plus u2 prime, y2 prime, plus u2, y2 second, plus pt times y prime, so pt times y1, u1, y1 prime, plus u2, y2 prime, and qt times y, that is qt times y, u1, y1, plus u2, y2. And we change things around in order to have the coefficients of y1 all together and the coefficients of y2 all together. And you might notice that these coefficients are exactly our homogeneous ODE. And the coefficient of u1 is our homogeneous ODE, our differential operator applied to one element of our fundamental set of solutions of the homogeneous ODE, and the coefficient of y2 is the other element applied to the differential operator of our homogeneous ODE. So these two parentheses tend to 0. That means that we simplified our problem from the general non-homogeneous ODE to the constraint that we added before, that is y1 prime, u1 prime, y1 plus u2 prime, y2 is equal to 0, and this simplification of L applied to y equals to our non-homogeneous term. So y1 prime, u1 prime plus u2 prime, y2 prime equals g of t. And here we have, again, an algebraic system. y1 prime and u1 prime and y2 prime appear in here always in that form. There is no derivative of y1 prime. So we can solve this, and we notice that u1 prime is equal to minus y2 gt divided by the Wronskian of y1 and y2. And u2 prime is y1 times gt divided by the same Wronskian. Now remember that the Wronskian of a fundamental set of solutions is different than 0 for all t. So we can compute the integral of y1 and y2. And we have coefficients appearing from these undefined integrals. So this confirms that choosing the variation of parameters does allow you to find a solution all the time. So let's look at a theorem that states everything that we have found until now. If functions p of t, q of t, and g of t are continuous on an open interval, then capital Y of t equals minus y1 times integral from t0 to t of y2 g divided by the Wronskian of y1 and y2 plus y2 integral from t0 to t of y1 g divided by the Wronskian of y1 and y2 dl. This is a particular solution, and y equals c1 y1 plus c2 y2 plus capital Y is the general solution.